The universe is expanding faster than anyone ever thought possible, not just at a steady pace, but accelerating, as if some invisible force is pushing it apart. This single discovery shattered centuries of assumptions about the cosmos and left scientists scrambling to rewrite the rules of physics. But it's just one of the countless revelations that have reshaped how we see the universe and our place within it. From the birth of stars to the echoes of the Big Bang, humanity has unlocked secrets that have fundamentally changed science, philosophy, and even the way we think about existence itself. In this video, we'll explore 20 groundbreaking space discoveries that didn't just add to our knowledge, they rewrote the story of everything. We'll start with a discovery so profound that it redefined the very scale of the universe. A revelation that revealed we are far smaller, and the cosmos far grander than anyone had ever imagined. Are you ready to see how these discoveries changed everything? Let's dive in. Picture this, a moment when time itself began, a single point of infinite density and heat exploding outward in a burst of light and energy. This wasn't just any explosion, it was the birth of the universe. The Big Bang Theory didn't just change how we see the cosmos, it rewrote the very story of existence. For centuries, many believed the universe was eternal and unchanging. But in the early 20th century, everything shifted. Edwin Hubble peered through his telescope and made a startling discovery. Galaxies were moving away from us, and the farther they were, the faster they retreated. This wasn't random motion, it was evidence that the universe itself was expanding. And if the universe was expanding, then tracing it backward meant it must have started from a single, unimaginably dense point. Then came the cosmic microwave background radiation, a faint glow discovered in 1965. This wasn't just static, it was the afterglow of the Big Bang, the faint echo of that first explosion. Together, these discoveries painted a picture of a universe that wasn't eternal but had a beginning, a moment when everything we know came into being. The implications were staggering. If the universe had a beginning, it raised questions about what came before and what might come after. Did time itself start with the Big Bang? Is the universe destined to expand forever, or will it one day collapse back in on itself? These are the questions that keep cosmologists awake at night, and they all trace back to that single, explosive moment. This discovery didn't just redefine cosmology, it reshaped how we think about our place in the cosmos. It showed us that the universe isn't static but dynamic, ever-changing, and full of mysteries waiting to be uncovered. And as we'll see, the Big Bang was just the beginning of a series of discoveries that would continue to transform our understanding of everything. Galaxies are supposed to behave in predictable ways. Stars on the outer edges should move slower than those near the center, much like planets in our solar system. Mercury zips around the Sun faster than Neptune. But when astronomers started measuring the speeds of stars in distant galaxies, they found something bizarre. Stars on the outer edges were moving just as fast, if not faster, than those near the center. This shouldn't be possible. According to the laws of gravity, galaxies would fly apart if only the visible matter, stars, gas, and dust were holding them together. Something unseen was at work, something massive enough to keep these galaxies intact. This invisible force became known as dark matter. The story of its discovery begins in the 1930s with Fritz Zwicky, a Swiss astronomer studying galaxy clusters. He noticed that galaxies within these clusters were moving far too quickly to be held together by just the visible matter they contained. He called this missing mass dark matter, though his ideas were largely dismissed at the time. Decades later, Vera Rubin and her colleague Kent Ford confirmed Zwicky's suspicions. By meticulously measuring the rotation curves of galaxies, they found the same puzzling behavior. Galaxies were spinning as if they were being held together by an invisible hand. Today, we know that dark matter makes up roughly 27% of the universe, 5 times more than all the ordinary matter we can see. It doesn't emit, absorb, or reflect light, which makes it nearly impossible to detect directly. Yet its gravitational effects are undeniable. Dark matter acts as a cosmic scaffolding, shaping the large-scale structure of the universe. Without it, galaxies might never have formed, and the universe as we know it would look entirely different. Despite decades of research, dark matter remains one of the greatest mysteries in science. What is it made of? Is it a particle or something entirely different? Experiments deep underground and in space are searching for answers, but so far, dark matter continues to elude us. Its existence forces us to confront how little we truly understand about the cosmos. And just as dark matter reshaped our understanding of gravity and the universe, there's another invisible force that's equally mysterious and equally game-changing. A force that's not holding the universe together but pushing it apart. Stay with us, because the next discovery will take us even deeper into the unseen forces shaping our reality. Just when scientists thought they had a handle on the universe's expansion, another curveball was thrown their way, one that would upend everything they thought they knew. In the late 1990s, astronomers studying distant supernova made a startling discovery. The universe wasn't just expanding, it was accelerating. This wasn't just surprising, it was downright baffling. According to the laws of physics, gravity should be slowing the expansion down, not speeding it up. So what was pushing the universe apart faster and faster? The answer was as mysterious as it was profound: dark energy. Dark energy is the name given to this unknown force, a kind of anti-gravity that permeates the cosmos. It's not pulling things together like dark matter, instead it's pushing them apart. The discovery came from observing Type 1, a supernova, which act as cosmic mile markers. By measuring their brightness, scientists can determine how far away they are and how fast the universe is expanding. What they found was shocking. The supernova were dimmer than expected, meaning they were farther away than they should have been. The universe wasn't just expanding, it was doing so at an ever-increasing rate. This revelation was so groundbreaking that it earned the researchers the 2011 Nobel Prize in Physics. But it also left us with more questions than answers. Dark energy makes up a staggering 68% of the universe's total energy content, dwarfing both dark matter and ordinary matter combined. Yet, despite its dominance, we still have no idea what it actually is. Is it a property of space itself, as Einstein once suggested with his cosmological constant? Or is it something entirely new, a force we've yet to even imagine? The implications are profound. If dark energy continues to accelerate the universe's expansion, it could lead to a future where galaxies are so far apart that the night sky becomes empty and dark. Stars would fade and the universe would grow cold and desolate, a fate cosmologists call the Big Freeze. But dark energy isn't just shaping the future of the universe, it's also challenging our understanding of physics as we know it. Here's the thing, dark energy and dark matter together make up 95% of the universe. That means everything we can see, stars, planets, galaxies, accounts for just 5% of the cosmos. It's a humbling reminder of how much we still have to learn. And as we'll see, these invisible forces aren't just reshaping our understanding of the universe, they're forcing us to rethink the very laws that govern it. So, what does this mean for the ultimate fate of the cosmos? And how do we even begin to study something we can't see or directly detect? The answers lie in the next chapter of our cosmic journey, where we'll explore how these mysteries are pushing the boundaries of science and our imagination. In the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were tinkering with a giant horn-shaped antenna in New Jersey. They were trying to eliminate a persistent static noise that seemed to come from every direction in the sky. No matter what they did, cleaning out pigeon droppings, adjusting equipment, the noise wouldn't go away. What they thought was a technical glitch turned out to be one of the most profound discoveries in the history of science. the cosmic microwave background radiation. This faint, omnipresent glow is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. At that time, the cosmos was a hot, dense soup of particles and energy. As the universe expanded and cooled, light was finally able to travel freely, leaving behind this faint echo. Today, that light has stretched into microwaves, filling the entire universe like a cosmic fingerprint. The discovery of this radiation was a smoking gun for the Big Bang theory. It provided concrete evidence that the universe had a beginning, a moment when everything we know burst into existence. But it didn't just confirm the Big Bang, it opened a window into the early universe. By studying the tiny fluctuations in this radiation, scientists have been able to map the large-scale structure of the cosmos. These fluctuations are like seeds, the tiny ripples that eventually grew into galaxies, galaxy clusters, and the vast cosmic web we see today. What's remarkable is how uniform this background radiation is. No matter where you look in the sky, the temperature varies by less than 1/1000th of a degree. Yet within that uniformity, those tiny variations tell a story of how the universe evolved from a chaotic, fiery beginning into the structured, star-filled expanse we see now. The cosmic microwave background radiation isn't just a relic of the past, it's a tool for understanding the present and predicting the future. It's been used to measure the age of the universe, 13.8 billion years, and to confirm the existence of dark energy and dark matter. It's a reminder that even the faintest whispers of the cosmos can reveal its deepest secrets. And speaking of whispers, the next discovery takes us even closer to the fundamental building blocks of the universe. What if I told you that everything around us, the stars, the planets, even you and me, is made of elements forged in the hearts of ancient stars? Stay with us, because the story of how the universe built itself is about to get even more fascinating. After the Big Bang, the universe was a dark, featureless expanse, a sea of gas with no stars, no galaxies, and no light. But then, something extraordinary happened. About 100 million years after the Big Bang, the first stars began to ignite, and the universe burst into light. This era, known as the Cosmic Dawn, marked the birth of the first stars and galaxies, a pivotal moment that would forever change the cosmos. These early stars weren't like the ones we see today. They were massive, hot, and short-lived, composed almost entirely of hydrogen and helium, the only elements present in the early universe. When they died, they exploded in spectacular supernova, seeding the cosmos with heavier elements like carbon, oxygen, and iron, the building blocks of everything that came after, including planets and life itself. But the birth of stars wasn't just about illumination. It also triggered a process called reionization. The intense ultraviolet light from these first stars and galaxies ionized the surrounding hydrogen gas, stripping electrons from atoms and transforming the universe from an opaque fog into the transparent expanse we see today. This was a cosmic turning point, setting the stage for the formation of galaxies, galaxy clusters, and the vast cosmic web. Telescopes like Hubble and James Webb have been instrumental in uncovering this ancient history. By peering deep into space and back in time, they've captured faint glimmers of these early galaxies, some so distant that their light has traveled over 13 billion years to reach us. The James Webb Space Telescope, in particular, has revolutionized our ability to study this era, revealing galaxies that formed just a few 100 million years after the Big Bang. These observations are like cosmic time capsules, offering a glimpse into the universe's infancy. What's fascinating is how these early structures laid the groundwork for the universe we know today. The first galaxies were the seeds of the cosmic web, the vast network of filaments and voids that spans the cosmos. Over billions of years, gravity pulled these galaxies together, forming clusters and superclusters, while the spaces between them grew emptier and darker. This intricate dance of gravity and light shaped the universe into the complex, dynamic structure we observe now. and yet there's so much more to uncover. How did these early galaxies grow and evolve? What secrets do they hold about the origins of the cosmic web? The answers lie in the next chapter of our journey, where we'll explore how the universe transformed from a chaotic, star-filled nursery into the organized, interconnected cosmos we see today. If the universe were a city, galaxies would be its neighborhoods clustered together in vast networks, connected by threads of gas and dark matter. This sprawling cosmic metropolis is known as the cosmic web, and it's one of the most awe-inspiring structures in existence. Stretching across billions of light years, the cosmic web is the backbone of the universe, a delicate tapestry woven by gravity over eons. The story of the cosmic web begins with the universe's earliest moments. After the Big Bang, tiny fluctuations in density, like ripples in a pond, created the seeds for future structures. Over billions of years, gravity pulled matter together, forming galaxies and galaxy clusters. But it didn't stop there. These clusters became connected by filaments of gas and dark matter, creating a vast, intricate network. Scientists first glimpsed this structure through computer simulations, which predicted how gravity would shape the distribution of matter. But it wasn't until the advent of powerful telescopes and surveys that they could see the cosmic web in action. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the web's stunning complexity. From dense knots where galaxies cluster to vast, empty voids, the cosmic web is a testament to the universe's dynamic nature. What makes the cosmic web so fascinating is its dual role in the universe's evolution. On one hand, it's a record of the past, a fossilized imprint of how gravity shaped the cosmos. On the other, it's a blueprint for the future, guiding the growth and movement of galaxies. Without this web, the universe would be a chaotic jumble, lacking the structure needed for galaxies to form and evolve. Yet, as breathtaking as the cosmic web is, it's just one piece of the puzzle. The universe isn't just a static network. It's a dynamic, ever-changing place shaped by violent and dramatic events. And that brings us to the next discovery, one that reveals the explosive forces that continue to shape galaxies and forge the elements that make life possible. At the heart of almost every galaxy lies a monster, a supermassive black hole, millions or even billions of times heavier than our Sun. These cosmic giants aren't just lurking in the shadows, they're actively shaping the galaxies they call home. Take our own Milky Way, for example. Hidden deep within its core is Sagittarius A, a supermassive black hole with a mass equivalent to 4 million suns. But how did we discover these invisible behemoths, and what role do they play in the grand story of the cosmos? The story begins with quasars, some of the brightest objects in the universe. In the 1960s, astronomers noticed strange, incredibly luminous objects that looked like stars but emitted enormous amounts of energy. These were quasars, powered by supermassive black holes devouring matter at an astonishing rate. As gas and dust spiral into the black hole, they heat up and glow so intensely that they outshine entire galaxies. Quasars became the first clues that supermassive black holes existed, and they revealed that these objects weren't just rare anomalies, they were widespread. But supermassive black holes aren't just cosmic vacuum cleaners. They're also architects shaping the galaxies around them. Their immense gravity can influence the orbits of stars, gas, and even other black holes. In some cases, they act like cosmic regulators, controlling the rate at which stars form. When a black hole feeds, it can unleash powerful jets of energy that heat up surrounding gas, preventing it from cooling and collapsing into new stars. This delicate balance between creation and destruction is one of the reasons galaxies like the Milky Way have the structure and size they do. Active galactic nuclei, or AN, are another key to understanding these black holes. These are the bright, energetic cores of galaxies where supermassive black holes are actively feeding. By studying AGNs, scientists have learned that black holes can go through cycles of activity and dormancy. Sometimes they're quiet and almost invisible, like Sagittarius are today. Other times they're ferocious, devouring everything in their path and lighting up the cosmos. What's truly mind-bending, though, is how supermassive black holes challenge our understanding of space and time. Their gravity is so intense that it warps the fabric of the universe, bending light and slowing time itself. Near the event horizon, the point of no return, the laws of physics as we know them break down. These objects force us to rethink not just how galaxies evolve, but how the universe itself operates on the most fundamental level. And as we'll see, black holes aren't just shaping galaxies. They're also leaving behind clues about the universe's most violent and dramatic events. From colliding black holes to ripples in spacetime, the next discovery will take us even deeper into the mysteries of gravity and the cosmos. In 2015, humanity witnessed a moment that would change the way we see the universe forever. For the first time, scientists detected gravitational waves, ripples in the very fabric of spacetime itself. These waves were caused by the collision of two black holes over 1 billion light-years away, an event so cataclysmic that it sent shockwaves through the cosmos. This discovery wasn't just a triumph of technology, it was a confirmation of a prediction made by Albert Einstein a century earlier. In his theory of general relativity, Einstein had theorized that massive objects like black holes could warp spacetime, creating ripples as they moved. But even he doubted we'd ever detect them. The detection was made by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a pair of massive detectors in the United States. Each detector is essentially a giant ruler, measuring distances so precisely that they can detect a change smaller than 1/10,000th the width of a proton. When the gravitational waves passed through Earth, they stretched and squeezed space itself, causing the detector's lasers to shift ever so slightly. The signal was faint but unmistakable, a cosmic whisper that confirmed Einstein's boldest ideas. This discovery didn't just validate a century-old theory, it opened an entirely new way of observing the universe. Before gravitational waves, we relied almost entirely on light, visible, radio, X-rays, to study the cosmos. But gravitational waves allow us to hear the universe, detecting events that might otherwise go unnoticed. For example, in 2017, LIGO detected gravitational waves from the collision of two neutron stars, an event that also produced a burst of light. This multi-messenger astronomy, combining gravitational waves and light, gave scientists a more complete picture of the event, revealing how heavy elements like gold and platinum are forged in the crucibles of such violent collisions. Gravitational waves aren't just a tool for studying black holes and neutron stars. They're a window into the most extreme environments in the universe. They allow us to probe the moments just before black holes merge, testing the limits of general relativity and even searching for hints of new physics. They've also given us a glimpse into the early universe, when gravitational waves from the Big Bang itself might have left an imprint on the cosmos. But the story of the universe's most violent events doesn't end with gravitational waves. These cosmic collisions leave behind more than just ripples, they scatter the building blocks of life itself across the cosmos. And that brings us to the next discovery, where we'll explore how the remnants of these explosive events shape the universe and make life as we know it possible. When a massive star exhausts its fuel and explodes in a supernova, it doesn't just vanish, it leaves behind a cosmic fingerprint, a dense, spinning remnant that defies imagination. These are neutron stars, the collapsed cores of once mighty stars, packed with more mass than our Sun into a sphere just a few miles across. A single teaspoon of neutron star material would weigh billions of tons, an almost incomprehensible density that pushes the limits of what matter can endure. The first neutron star was discovered in 1967, and it came with a twist. astronomers Jocelyn Bell Burnell and Anthony Hewish detected a strange, rhythmic signal from deep space, a series of pulses so precise they initially wondered if they'd stumbled upon evidence of extraterrestrial intelligence. What they'd actually found was a pulsar, a rapidly spinning neutron star that beams radiation like a cosmic lighthouse. As the star spins, its beams sweep across the sky, creating the regular pulses that make pulsars so distinctive. These pulsars aren't just fascinating cosmic oddities, they're also incredibly useful tools. Because their pulses are so regular, they've been used as natural clocks to test some of the most fundamental theories in physics. For example, the famous Hulse-Taylor binary pulsar, discovered in 1974, provided the first indirect evidence of gravitational waves. By carefully tracking the pulses from this system, scientists observed that the two neutron stars were slowly spiraling closer together, exactly as Einstein's theory of general relativity predicted. But neutron stars and pulsars aren't just cosmic timekeepers, they're also cosmic forgers. When neutron stars collide, they unleash some of the most violent and energetic events in the universe. These collisions are so powerful that they can create heavy elements like gold, platinum, and uranium, scattering them across the cosmos. In fact, much of the gold in your jewelry or the uranium used in nuclear reactors likely originated in the aftermath of a neutron star collision billions of years ago. Yet, for all we've learned, neutron stars remain some of the most mysterious objects in the universe. Their extreme density and gravity create conditions that are impossible to replicate on Earth, forcing scientists to rethink how matter behaves under such pressure. What happens to the protons and electrons inside a neutron star? Could there be even stranger forms of matter like quark-gluon plasma hiding within their cores? These are questions that push the boundaries of our understanding and hint at how much we still have to learn about the universe's most extreme environments. And as we'll see, neutron stars aren't the only exotic objects challenging our understanding of matter. The next discovery takes us even deeper into the strange and unpredictable nature of the cosmos, where the rules of physics as we know them begin to break down. For centuries, planets were thought to exist only around our sun. But in 1995, that assumption was shattered when astronomers Mitchell Mayer and Didier Queloz discovered something extraordinary, a planet orbiting a star 50 light-years away. This wasn't just any planet, it was 51 Pegasi b, a gas giant so close to its star that it completes an orbit in just 4 days. The discovery was revolutionary, proving that our solar system wasn't unique. Planets could exist around other stars, and they came in all shapes and sizes. Fast forward to today, and we've found over 5,000 confirmed exoplanets, with thousands more waiting to be verified. Missions like NASA, Kepler, and TESS have transformed our understanding of these distant worlds. Kepler, for example, stared at a single patch of sky for years, detecting tiny dips in starlight as planets passed in front of their stars. This method, called the transit technique, has revealed planets ranging from scorching hot Jupiters to rocky, Earth-sized worlds. But the real game-changer has been the discovery of planets in the habitable zone, the Goldilocks region around a star where temperatures might allow liquid water to exist. Kepler 452b, for instance, is often dubbed Earth's cousin, orbiting a Sun-like star at just the right distance. Then there's Proxima Centauri b, the closest known exoplanet to us, located just over 4 light-years away. Could these worlds host conditions suitable for life? The possibility is tantalizing. Exoplanets aren't just about finding new real estate in the universe, they're about understanding our place in it. By studying their atmospheres, we've detected gases like water vapor, methane, and even oxygen potential biosignatures that could hint at life. Future telescopes, like the James Webb Space Telescope, are poised to take this search to the next level, analyzing the chemical fingerprints of distant worlds in unprecedented detail. What's truly remarkable is how quickly this field has evolved. In less than 30 years, we've gone from not knowing if other planets existed beyond our solar system to mapping an entire galaxy of possibilities. Each new discovery brings us closer to answering one of humanity's most profound questions. Are we alone? But the search for life doesn't end with planets. To truly understand the origins of life in the universe, we need to explore the very ingredients that make it possible. And that's where the next discovery takes us into the cosmic chemistry lab, where the building blocks of life are scattered across the stars. Deep within the vast clouds of gas and dust that drift between the stars, something extraordinary is happening chemistry on a cosmic scale. These interstellar clouds, often called stellar nurseries, are more than just the birthplaces of stars and planets. They're also immense chemical factories producing some of the most complex molecules in the universe. And not just any molecules, organic ones, the very building blocks of life. The first hints of this cosmic chemistry came in the 1960s, when radio telescopes detected simple molecules like formaldehyde and ammonia in space. At the time, this was a shock. Space was supposed to be empty, right? But as technology improved, astronomers began discovering more and more complex molecules, including amino acids, the key components of proteins. These discoveries revealed that the ingredients for life aren't confined to Earth, they're scattered throughout the cosmos. Comets, those icy visitors from the outer solar system, have also played a starring role in this story. When the European Space Agency's Rosetta mission landed on Comet 67P in 2014, it uncovered a treasure trove of organic molecules, including glycine, a simple amino acid. This was a game changer. It showed that comets, which bombarded the early Earth, could have delivered the raw materials for life to our planet billions of years ago. These findings have profound implications. If organic molecules are common in space, then the conditions for life might be widespread too. It's not just about Earth anymore, it's about the entire universe. Every star with planets, every swirling cloud of gas and dust could be a potential cradle for life. But the story doesn't end there. These molecules aren't just passive ingredients, they're active players in the universe's chemistry. Under the right conditions, they can combine and react, forming even more complex structures. Some scientists believe that the seeds of life, simple, self-replicating molecules, could form right in the heart of these cosmic clouds long before they ever reach a planet. What's truly exciting is how this connects to the search for life beyond Earth. If the building blocks of life are everywhere, then the chances of finding life elsewhere in the universe just got a lot higher. Whether it's on a distant exoplanet, a moon in our own solar system, or even floating freely in space, the potential for life is greater than we ever imagined. And as we'll see next, the search for life isn't just about finding molecules, it's about finding the right environments where those molecules can come together and thrive. The universe is vast, but the clues are out there waiting to be discovered. For centuries, Mars has captivated our imagination, a barren red world that seemed as lifeless as it was distant. But in recent years, our robotic explorers have revealed a startling truth. Mars wasn't always the dry, desolate planet we see today. Beneath its rusty surface lies evidence of a watery past, one that could rewrite our understanding of the red planet and its potential to support life. The first clues came from orbiters like NASA Mars Reconnaissance Orbiter, which spotted ancient riverbeds, deltas, and lake beds etched across the Martian landscape. These features, some as wide as the Mississippi River, told a story of a planet that once had flowing water, possibly even oceans. But the real game changer came in 2018, when the European Space Agency's Mars Express spacecraft detected liquid water beneath the planet's south pole. Using radar, scientists found a massive underground lake buried beneath layers of ice and dust. This wasn't just a relic of the past, it was a reservoir that could still exist today. Rovers like Curiosity and Perseverance have added even more to this watery tale. Curiosity's exploration of Gale Crater revealed sedimentary rock layers that could only have formed in the presence of water. Perseverance, meanwhile, has been busy collecting samples from an ancient delta in Jezero Crater, a site that was once a thriving lake. These samples, which will eventually be returned to Earth, could contain clues about whether life ever existed on Mars. The implications are profound. If Mars once had liquid water, and possibly still does, it raises the tantalizing possibility that life could have emerged there too. Even more exciting is what this means for future human exploration. Water isn't just essential for life, it's a vital resource for astronauts, providing drinking water, oxygen, and even fuel. The discovery of water on Mars makes it a realistic destination for human missions, potentially paving the way for a permanent presence on the red planet. But Mars isn't the only place in our solar system where water holds secrets. Beyond the red planet, in the icy reaches of our cosmic neighborhood, lie moons that might harbor oceans far larger than those on Earth. These frozen worlds, hidden beneath their icy shells, could be the next frontier in our search for life, and they're even more mysterious than Mars. What could these hidden oceans reveal about the potential for life beyond Earth, and how do they change our understanding of where life might exist in the universe? The answers lie in the next chapter of our cosmic journey, where we'll dive into the icy moons of Jupiter and Saturn, worlds that might just hold the keys to unlocking the mysteries of life itself. When we think of oceans, we often picture vast, blue expanses on Earth. But what if I told you that some of the most intriguing oceans in our solar system aren't on Earth at all? They're hidden beneath the icy crusts of moons orbiting Jupiter and Saturn. This discovery, one of the most exciting in planetary science, has reshaped how we think about where life might exist in the universe. Let's start with Europa, one of Jupiter's largest moons. For decades, scientists suspected that Europa might have a subsurface ocean, but it wasn't until the late 1990s that the Galileo spacecraft provided concrete evidence. As it flew by Europa, Galileo detected a magnetic field, something that shouldn't exist on a solid, icy moon. The explanation: a salty, liquid ocean beneath the ice acting as a conductor. This ocean isn't just a thin layer, it's estimated to be 60 miles deep, holding twice as much water as all of Earth's oceans combined. Then there's Enceladus, a small but mighty moon of Saturn. When the Cassini spacecraft arrived at Saturn in 2004, it made an astonishing discovery: geysers of water erupting from cracks in Enceladus's icy surface. These plumes, shooting hundreds of miles into space, contain not just water but also organic molecules like methane and carbon dioxide. Even more intriguing, Cassini detected tiny grains of silica in the plumes, suggesting the presence of hydrothermal vents on the ocean floor, places where heat and minerals interact, creating environments that could support life. What makes these discoveries so groundbreaking is their potential for habitability. On Earth, hydrothermal vents are teeming with life, hosting ecosystems that thrive in complete darkness. If similar vents exist on Enceladus or Europa, could they also harbor life? The conditions seem promising. Both moons have the three key ingredients for life as we know it: liquid water, organic molecules, and a source of energy. But these moons don't just challenge our understanding of where life might exist, they also redefine what we consider a habitable environment. For years, the habitable zone was defined as the region around a star where liquid water could exist on a planet's surface. Europa and Enceladus, however, lie far outside this zone, in the frigid outer reaches of the solar system. Yet, thanks to the heat generated by tidal forces, the gravitational tug of war between the moons and their parent planets, they maintain liquid oceans beneath their icy shells. This discovery forces us to rethink the very concept of habitability. Could life exist in the most unexpected places, far from the warmth of a star? And if so, what does that mean for the search for life beyond our solar system? The answers might lie in the next chapter of our cosmic journey, where we'll explore how these icy moons are just the beginning of a much larger story, one that stretches across the galaxy and beyond. Far beyond the familiar planets and the icy moons of Jupiter and Saturn lies a vast, mysterious frontier, a region so distant and faint that it's only recently come into focus. This is the Kuiper Belt, a ring of icy bodies orbiting the Sun beyond Neptune, and the even more distant Oort Cloud, a spherical shell of frozen debris that stretches nearly halfway to the next star. These distant reservoirs are more than just cosmic curiosities. They're the remnants of our solar system's birth, holding clues to how everything we know came to be. The Kuiper Belt was first theorized in the mid-20th century, but it wasn't until 1992 that astronomers confirmed its existence. Using powerful telescopes, they spotted a small, icy world orbiting far beyond Neptune, an object now known as 1992 QB1. Since then, thousands of similar objects have been discovered, including Pluto, which was reclassified as a Kuiper Belt object in 2006. These icy bodies are like cosmic time capsules, preserving the raw materials from which the solar system formed over 4.5 billion years ago. But the Kuiper Belt is just the beginning. Beyond it lies the Oort Cloud, a hypothetical region of icy debris that extends up to a light year from the Sun. Unlike the flat, disk-like Kuiper Belt, the Oort Cloud is thought to be a spherical shell surrounding the solar system like a cosmic cocoon. While we've never directly observed the Oort Cloud, it's too faint and far away. Its existence is supported by the orbits of long-period comets, which swing into the inner solar system from all directions. These comets are more than just dazzling celestial fireworks. They're messengers from the solar system's edge. When a comet's icy nucleus gets nudged by a passing star or the gravitational pull of the Milky Way, it begins a long journey toward the Sun. As it approaches, the heat causes the ice to vaporize, creating the glowing coma and tail we associate with comets. But what's truly remarkable is that these comets carry with them the original ingredients of the solar system: water, organic molecules, and even the building blocks of life. The discovery of the Kuiper Belt and the Oort Cloud has fundamentally changed how we think about the solar system's formation. They're evidence of the chaotic early days when the Sun's gravity pulled in gas and dust, forming planets and scattering the leftovers into the distant reaches of space. Without these icy reservoirs, we wouldn't have comets, and without comets, life on Earth might never have gotten the water and organic molecules it needed to thrive. But the story doesn't end at the edge of the Oort Cloud. Beyond this frozen frontier lies an even greater mystery: the boundary where our solar system meets the vast expanse of interstellar space. What lies out there, and how does it shape our cosmic neighborhood? The next discovery takes us to the very edge of the Sun's influence, where the solar wind gives way to the stars. In 2012, humanity achieved something extraordinary, a feat that marked the first time anything made by human hands had ventured beyond the influence of our Sun. Voyager 1, a spacecraft launched in 1977 to explore the outer planets, had traveled over 11 billion miles from Earth and crossed into interstellar space. This wasn't just a milestone for space exploration. It was a moment that redefined our understanding of the solar system's boundaries and our place within the cosmos. The key to this discovery lies in the heliopause, the invisible boundary where the solar wind, a stream of charged particles flowing from the Sun, meets the interstellar medium, the gas and dust that fills the space between stars. For years, scientists debated where exactly this boundary lay, but Voyager 1 provided the answer. In August 2012, its instruments detected a dramatic drop in solar particles and a corresponding increase in cosmic rays from interstellar space. This was the smoking gun. Voyager 1 had crossed the heliopause, becoming the first human-made object to enter the realm of the stars. The data Voyager 1 sent back was nothing short of revolutionary. It revealed that the heliopause isn't a sharp, clean boundary, but a dynamic, turbulent region where the solar wind and interstellar medium interact. This discovery has reshaped our understanding of how the Sun's influence extends and where it ends. It's also given us a glimpse into the interstellar environment, a region that's crucial for understanding how stars and galaxies form. But Voyager 1 journey is more than just a scientific triumph. It's a testament to human ingenuity and curiosity. Built with 1970s technology, the spacecraft has far outlived its original mission, continuing to send data back to Earth even as its power dwindles. Its golden record, a time capsule of sounds and images from Earth, carries a message to any potential extraterrestrial civilizations that might one day find it, a hopeful reminder of our desire to connect with the universe. What's truly inspiring about Voyager 1 is how it embodies the spirit of exploration. It reminds us that the boundaries we once thought were fixed are only the beginning of what's possible. As we look to the future, missions like Voyager 1 pave the way for new journeys, ones that might take us even farther into the unknown, to worlds and stars we've only begun to imagine. And as we'll see, the next discovery takes us beyond the solar system entirely, to a realm where planets orbit distant stars and where the search for life begins anew. In 1995, the Hubble Space Telescope aimed its lens at what seemed like an unremarkable patch of sky, a dark, seemingly empty region no larger than a grain of sand held at arm's length. What it revealed, however, was anything but empty. This single image, known as the Hubble Deep Field, captured something extraordinary. Thousands of galaxies, each a swirling island of stars, gas, and dust, stretching back billions of years into the universe's past. The Hubble Deep Field wasn't just a photograph, it was a cosmic revelation. For the first time, we could see the universe on a scale that was almost beyond comprehension. Every speck of light in that image represented not just a galaxy, but an entire universe of possibilities. Some of these galaxies were among the youngest ever observed, their light traveling for over 13 billion years to reach us. Others were faint and distant, their shapes distorted by the expansion of the universe itself. What made this discovery so groundbreaking was the sheer number of galaxies it revealed. Before the Hubble Deep Field, astronomers estimated there were around 10 billion galaxies in the observable universe. But this image suggested there could be hundreds of billions, maybe even trillions, each containing billions of stars. The universe wasn't just vast, it was unimaginably vast, filled with more galaxies than grains of sand on all the beaches of Earth. But the Hubble Deep Field did more than just expand our understanding of the universe's scale. It also deepened our sense of wonder. For many, it was a humbling reminder of how small we are in the grand scheme of things. Yet, at the same time, it sparked a profound curiosity: what lies beyond these galaxies? What secrets do they hold about the origins of the universe? This image also marked a turning point in astronomy. It showed that even the emptiest-looking regions of the sky are teeming with galaxies, each with its own story to tell. Follow-up observations like the Hubble Ultra Deep Field and the Extreme Deep Field have only added to this cosmic tapestry, revealing galaxies so distant that we're seeing them as they were just a few 100 million years after the Big Bang. The Hubble Deep Field didn't just change how we see the universe, it changed how we see ourselves. It reminded us that we're part of something much larger, a universe that's both beautiful and bewildering in its complexity. And as we gaze deeper into the cosmos, we're left with even more questions, like why the universe is expanding faster than we ever expected, and what that means for its ultimate fate. That brings us to the next discovery, one that takes us even deeper into the mysteries of the universe's expansion and the invisible force driving it. The universe we once thought was expanding, but slowly, steadily, as if it were coasting on the momentum of the Big Bang. Then, in 1998, everything changed. Two teams of astronomers studying distant supernova made a discovery so shocking it would redefine our understanding of the cosmos. the universe isn't just expanding, it's accelerating. And the force behind this acceleration, a mysterious, invisible entity we now call dark energy. To understand why this was so groundbreaking, let's rewind a bit. For decades, scientists had assumed that gravity, the force that pulls matter together, would eventually slow the universe's expansion, but the data told a different story. By measuring the brightness of Type 1, a supernova exploding stars that act as cosmic yardsticks, the researchers found that these supernovae were dimmer than expected. That meant they were farther away than they should have been, implying that the space between galaxies was stretching faster and faster over time. Dark energy was the only explanation that fit. Unlike dark matter, which pulls things together with its gravity, dark energy seems to push the universe apart, acting as a kind of anti-gravity. It's not just a small effect. Either dark energy makes up about 68% of the universe's total energy content. That's more than twice the amount of dark matter and 5 times more than all the ordinary matter we can see. This discovery didn't just earn the researchers a Nobel Prize, it upended our understanding of gravity and the fundamental forces shaping the cosmos. Einstein's theory of general relativity, which had predicted the existence of something like dark energy through his cosmological constant, suddenly became relevant again. Yet, even with this theoretical framework, dark energy remains one of the greatest mysteries in science. What is it made of? Is it a property of space itself, or something entirely different? The implications of dark energy are profound, not just for the universe's past, but for its future. If this acceleration continues, galaxies will eventually move so far apart that they'll disappear from view, leaving behind a cold, dark, and empty cosmos, a scenario cosmologists call the Big Freeze. But there's also the possibility that dark energy could evolve over time, leading to even more dramatic outcomes like the Big Rip, where the fabric of spacetime itself is torn apart. To unravel these mysteries, scientists are working tirelessly to measure the Hubble constant, the rate at which the universe is expanding. But here's the catch: different methods of measuring this constant keep giving slightly different results. This Hubble tension has sparked intense debate, with some suggesting it could hint at new physics beyond our current understanding. What's fascinating is how this discovery connects to the very origins of the universe. If dark energy has been shaping the cosmos since the beginning, it raises questions about the Big Bang itself, and whether the universe's expansion could one day reverse or take an entirely unexpected turn. As we continue to probe the mysteries of dark energy, we're left with a humbling truth: the universe is far stranger and more dynamic than we ever imagined. And just as dark energy reshapes the cosmos, it's also reshaping our understanding of existence itself. But the story doesn't end there. To fully grasp the universe's origins, we need to look back even further, to a time when the cosmos was just a tiny, searing point of energy. The next discovery takes us to the very beginning, where the seeds of everything we see today were first sown. What if our universe isn't the only one? What if, beyond the boundaries of space and time, there are countless other universes, each with its own laws of physics, its own stars, and maybe even its own versions of us? This isn't science fiction, it's the multiverse theory, one of the most provocative and controversial ideas in modern cosmology. The concept of a multiverse didn't come out of nowhere. It's rooted in some of the most advanced theories in physics, including cosmic inflation and string theory. Cosmic inflation, for example, suggests that in the moments after the Big Bang, space expanded faster than the speed of light. But what if that expansion didn't stop everywhere at once? What if pockets of space kept inflating, creating bubble universes that are now completely separate from our own? String theory, on the other hand, proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings of energy. These strings could exist in higher dimensions up to 11, according to some versions of the theory, and these dimensions could host other universes, each with its own unique set of physical laws. The implications of the multiverse theory are staggering. If true, it means that everything we see, our galaxy, our planet, even ourselves, might be just one of an infinite number of possibilities. Some universes might have stronger gravity, making stars burn out faster. Others might lack the conditions for life altogether. And in some, the constants of nature, like the speed of light or the charge of an electron, might be completely different, leading to realities that are utterly alien to us. But here's the catch: we can't see these other universes. They exist beyond the observable universe, hidden by the very fabric of space-time. This makes the multiverse theory impossible to test directly, at least with our current technology. For some, that's a problem. How can we study something we can't observe? For others, it's an invitation to rethink what science can and should explore. The multiverse theory doesn't just challenge our understanding of the cosmos, it raises profound philosophical questions. If there are infinite universes, does that mean every possible version of reality exists somewhere? Could there be a universe where dinosaurs never went extinct, or where humanity never evolved? And if so, what does that mean for our sense of uniqueness and purpose? Of course, not everyone is convinced. Critics argue that the multiverse theory is more speculation than science, a way to explain away the fine-tuning of our universe without offering testable predictions. But even its skeptics admit that the idea has pushed cosmology in bold new directions, forcing us to confront the limits of our understanding. And speaking of limits, the multiverse theory isn't the only idea pushing the boundaries of human knowledge. It's part of a larger quest to explore the ultimate questions. What is the nature of reality, and how far can our curiosity take us? The next discovery takes us even further into the unknown, where the very fabric of space and time begins to unravel. The universe is vast, but even its vastness has boundaries that are not just physical, but deeply tied to the very nature of time and light. These boundaries are known as the cosmic horizon, the farthest point we can possibly see. Beyond this horizon lies a portion of the universe that is, and may forever remain, hidden from us. This isn't just a limitation of technology or distance. It's a fundamental consequence of the universe's age and the speed of light. The cosmic horizon exists because light takes time to travel. Since the Big Bang occurred roughly 13.8 billion years ago, the light from the farthest reaches of the universe has had only that much time to reach us. Anything beyond that distance, beyond the cosmic horizon, is essentially invisible to us because its light hasn't had enough time to make the journey. It's like standing on the shore of an ocean, watching the waves roll in, but knowing there's an entire unseen expanse beyond the horizon. But here's where it gets even more fascinating. The universe itself has been expanding since the Big Bang, stretching space and carrying galaxies along with it. This means that the light from distant objects is not only traveling toward us, but also being stretched by the expansion of space itself. As a result, the light from the earliest moments of the universe arrives not as visible light but as faint microwaves, part of what we call the cosmic microwave background. This background radiation is our deepest glimpse into the past, but it's also a reminder of how much of the universe lies beyond our view. What lies beyond the cosmic horizon? We can't know for sure. It could be more galaxies, more stars, and even more mysteries. Or it could be something entirely different, regions of space where the laws of physics as we know them break down or take on new forms. The cosmic horizon isn't just a barrier to observation. It's a boundary that sparks curiosity and fuels imagination. This limitation has profound philosophical implications. It forces us to confront the idea that there are parts of the universe we may never fully understand. No matter how advanced our technology becomes, it challenges the very notion of what it means to explore and discover. Are we, as a species, destined to only ever see a fraction of what exists? And if so, what does that say about our place in the cosmos? Yet, rather than being a source of frustration, the cosmic horizon inspires new questions and new ways of thinking. It pushes scientists to develop creative methods for probing the universe's secrets, from studying gravitational waves to searching for indirect clues in the cosmic microwave background. It reminds us that exploration is not just about what we can see, but about what we can imagine and theorize. And as we grapple with these limits, we're reminded that the universe is not just a collection of objects we can observe. It's a dynamic, evolving story, full of mysteries waiting to be uncovered. The cosmic horizon isn't the end of that story. It's a gateway to new chapters, new discoveries, and new ways of understanding the cosmos. But what if the universe isn't just expanding? What if it's also evolving in ways we can't yet comprehend? The next discovery takes us even deeper into the mysteries of the cosmos, where the very fabric of reality itself might be undergoing transformations we've only begun to imagine. For thousands of years, humanity has gazed at the stars and wondered, are we alone? It's a question that has fueled our imagination, inspired countless stories, and driven us to explore the cosmos. But it's no longer just a philosophical musing, it's a scientific endeavor. Today, we're actively searching for signs of intelligent life beyond Earth, and projects like SETI, the search for extraterrestrial intelligence, are at the forefront of this quest. SETI, launched in the 1960s, uses powerful radio telescopes to scan the skies for signals that might indicate the presence of advanced civilizations. The idea is simple. If there are intelligent beings out there, they might be sending out signals just as we do with radio and television broadcasts. Over the decades, SETI has sifted through billions of frequencies, searching for patterns that stand out from the cosmic noise. While no definitive signal has been found yet, the search continues, fueled by the tantalizing possibility that we might one day make contact. More recently, the Breakthrough Listen initiative has taken this search to new heights. Funded by billionaire Yuri Milner, Breakthrough Listen uses some of the world's most advanced telescopes to scan millions of stars and galaxies for signs of technological activity. It's the most comprehensive search for extraterrestrial intelligence ever undertaken, and it's already produced intriguing results, including a mysterious signal from Proxima Centauri, the closest star system to our own. While the signal remains unexplained, it's a reminder that the universe is full of surprises and that we're only just beginning to explore its possibilities. But what would it mean if we actually found evidence of intelligent life? The implications would be profound, reshaping not just science but philosophy, religion, and culture. It would force us to confront our place in the universe, challenging the notion that we're unique or special. At the same time, it could unite humanity in a shared sense of wonder, reminding us that we're part of something much larger. This search for extraterrestrial intelligence is more than just a scientific endeavor. It's a reflection of our deepest hopes and fears. It's about the desire to connect, to understand, and to know that we're not alone in the vastness of space. And while we may not find answers anytime soon, the search itself is a testament to our curiosity and our determination to explore the unknown. From the Big Bang to the cosmic web, from black holes to distant exoplanets, the discoveries we've explored today have fundamentally reshaped how we see the universe and our place within it. Each revelation has reminded us that the cosmos is far stranger, more dynamic, and more interconnected than we ever imagined. And as we continue to push the boundaries of knowledge, we're not just uncovering the secrets of the universe, we're uncovering the story of ourselves. So, what's next? The universe is full of mysteries waiting to be solved, and the journey is far from over. The search for life, the exploration of distant worlds, and the quest to understand the very fabric of reality, these are the questions that will drive us forward, inspiring generations to come. The cosmos is vast, but so is our curiosity, and as long as we keep looking up, the discoveries will never end. From the explosive birth of the universe in the Big Bang to the invisible threads of dark matter weaving galaxies together, the 20 discoveries we've explored today have fundamentally reshaped how we see the cosmos. They've revealed a universe that's not static but dynamic, not simple but infinitely complex, and not just vast but teeming with mysteries waiting to be uncovered. Each revelation has been a step forward in our journey to understand our place in the grand tapestry of existence. These discoveries have done more than expand our knowledge, they've transformed science itself. The Big Bang Theory rewrote the story of the universe's origins, showing us that everything we know began in a single, fiery moment. Dark matter and dark energy, though still shrouded in mystery, have forced us to rethink the very laws of physics, revealing that most of the universe is made of stuff we can't even see. Gravitational waves opened a new way to observe the cosmos, allowing us to hear the collisions of black holes and neutron stars. And the search for exoplanets has shown us that Earth is just one of countless worlds orbiting distant stars, some of which might even harbor life. But the impact of these discoveries goes beyond science. They've sparked profound philosophical questions about our place in the universe. Are we alone? What lies beyond the cosmic horizon? Could there be other universes, each with its own set of rules? These aren't just academic questions, they're deeply human ones, touching on our sense of wonder, curiosity, and purpose. And then there's the practical side. The search for water on Mars and the exploration of icy moons like Europa and Enceladus aren't just about finding life, they're about preparing for humanity's future. These missions could pave the way for human exploration and even colonization of other worlds, ensuring our survival as a species and expanding the boundaries of what's possible. As we stand on the brink of new discoveries, it's worth reflecting on how far we've come. Just a century ago, we didn't even know other galaxies existed. Today, we're mapping the cosmic web, probing the edges of black holes and searching for life beyond Earth. It's a testament to human ingenuity and our unquenchable thirst for knowledge. But the journey isn't over. The universe is vast and its mysteries are endless. Every discovery raises new questions, and every question leads us deeper into the unknown. That's the beauty of science. It's a never-ending adventure, one that invites us all to explore, question, and wonder. So, what's your role in this cosmic story? Whether you're an astronomer, a student, or just someone who loves to gaze at the stars, you're part of this journey. Share your thoughts, ask questions, and stay curious. The universe is full of secrets waiting to be uncovered, and the next great discovery could be just around the corner. Keep looking up, keep exploring, and remember, the cosmos is vast, but so is our potential to understand it. The adventure is just beginning.